So we have a population that we are studying. Let's say it's bees in a park, okay? And each season we have that 40% of them die, all right? So 40% of the bees die each season, but we also add 20 additional newbies by the beekeeper. So if we let T represent the number of seasons and X of T will be the bee population at season T, we are asked to find the following, okay, starting with the updating function. So if we look at the population of bees, that is going to be next season, right? So T represents the season, so XT plus 1 is next season. Well, what do we see? We see that 40% of them die. So 40% of them die, that means that 60% of them stay, right? That means that 60% of them stay. So then we have 60%, or you can say 6 on 10, 6 on 10 times XT, okay? This means that the bees next season, right, XT plus 1, is going to be 60% of the bees this season, right? Because 40% of them, 4 over 10, die, okay? But we also add 20 additional bees, okay? So this is our discrete time dynamical system here. And if we want the updating function, we just call this thing f of x, and f of x becomes 6 over 10 x plus 20. And that's our answer for B. For A, sorry. Now, part B, if at the start of the season we have 100 bees, okay, so that just gives us our initial value. X naught is 100. Okay, compute the number of bees we have after 1, 2, and 3 seasons. So basically, we're asked to find X1, X2, and X3. All right, so we could do this in 2 ways. First way is we can actually use, because this system is of the form, the updating function is of the form Rx plus D, we can actually go ahead and use this equation that X of T is going to be equal to R to the T times X minus X star, sorry, X naught minus X star plus X star, where X star is the equilibrium. We could do that. And that's going to allow us to find the population of bees at any time T. But because we're only asked to do after 1, 2, and 3 seasons, in this case, it'll be a lot faster, and we're going to have to do this thing anyway, but it'll be a lot faster and good practice to just apply the updating function. So we know that x1, right, is going to be f of x naught, right? We put in x naught, the initial number of bees, into the updating function here, and we get x naught plus 1, that is to say x1. Okay, so we do that, put it in the updating function, and what do we get? Well, we're going to get that x1 is equal 6 over 10 times 100. That's 60 plus 20. So we're going to get that x1 is equal to, this is going to be 60 plus 20 is going to be 80 bees. So x1 is 80. All right, now let's put 80 into the updating function. So x2 is going to be f of x1, right? Because the updating function is going to update x1 into x2. That's what it does. So we're going to get that x2 is equal to 6 over 10 times 80 plus 20. Let me just get the calculator out for these. So I am lazy. 6 over 10 times 80 plus 20. It's going to be 68 bees. So x2 is going to be 68 bees. All right. And the next 3, so after 3 seasons, it's going to be f of x2. So x3 is going to be 6 over 10 times 68 plus 20. So it's going to be 6 over 10, so 0.6 times 68 plus 20. It's going to be 60.8 bees. All right, so that is part B. Part C, we find the fixed point, the equilibrium. So the equilibrium is when our updating function f of x is equal to x. The updating function is 6 over 10x plus 20, and we want that equal to x is equal to 20. And so x star is going to be 200 divided by 4. It's going to be 50. The equilibrium population is 50 bees. Okay, another way of solving it is because the updating function takes the form f of x is equal to rx plus d. Okay, you know that the equilibrium we derived this earlier, is going to be d over 1 minus r. So it's going to be, well, what's d in this case? D is 20. 20 over 1 minus 6 over 10. So that's 1 minus 6 over 10. That's 4 over 10. So it's 20 over 4 over 10. So that's 200 divided by 4, which is 50. Okay, both approaches give you the same answer. All right, so that's part C. And then part D, write the general solution. So the general solution in part D is going to be of the form xt is equal to r to the t x naught minus x star plus x star, right? And our updating function, of course, this general solution only applies to updating functions of the form rx plus d. And so what that means is if we match our updating function, we obviously see that x is 6 over 10, and d is 20, right? And so what we can do is we can therefore say that x of t, just plug it into here, we get 6 over 10 to the power of t. Okay, x naught, the initial population of bees we were told was 100 right over here. So 100 minus 50, which is, well, 50, plus the equilibrium population, which is 50. So therefore we have the x of t, the population of bees, the general solution, is 6 to the 10 times t times 50 plus 50. Our general solution right over here. And what I can do is I can actually go into Desmos and I can plot it over here. Say x of t is this thing right over here. Okay. And I can evaluate x of 0, which expectedly gives us 100, x of 1 gives us 80, x of 2 gives us 68, and x of 3, well, it gives us the 60.8 right there.